Okay, okay, assholes, here we are. I'm going to give you a little run through on a sort of a standard kind of an engineering problem that you might be faced with. It involves an electric drill. You've seen them all. Wait a minute. And there it is. There's the drill. And let's just say, for the sake of argument, it's putting out, or designed to put out, 10 foot-pounds of torque one way, and there's reaction back on your hand. And so, at the level of the drill, the torques are balanced. That's fine. And that's what the bottom two bullets, top two bullets say in the bottom. And we're balanced there for that's man-machine interface. And you can also think about the fact that there's a torque that's on the wall that the drill is putting into the wall as you're drilling it. And that goes onto the wall, to the floor, and back up to the man's feet and back up to the man's hands. So the whole torque system is balanced throughout that path, that circular path. Okay? So we got, this kind of just repeats what I've just said, sets up the problem here. And it's balanced. So you're a design engineer, and the drill motor produces 1 pound of reaction torque on the drill case. Fair enough, that's the size of the thing. And there's a 10-to-1 gear ratio or transmission between the motor and the chuck. Okay? And that's where the 10 foot-pounds of will come. But where's the other 9 pounds coming from to make up the back reaction on the drill case? Right? I mean, you've got one on the motor reaction, and then you've got 9 coming out. But where's the 9 coming out on the shaft, or out on the handle of the case? Because there's no torque on the shaft going through the outboard bearing where the chuck is. So you've got 10 foot-pounds on your handle, and then there's 1 from the motor. And so where's the other 9 coming from? Okay, so there's a situation there. So let's just say that that's the situation. And where's the other 9 foot-pounds of torque? So let's just look at this thing, and we've got these various forces. This represents the gear train. It's not the scale, but the force at the teeth from the pinion and into the big torque gear are balanced. So those two forces are balanced. And one is at radius, one radius, and the other one is at the larger radius. And the total distance between them is this RC plus RP, pinion and chuck gear thing. Okay? So, it turns out that when you do that, as you might think, there's going to be a torque on the gearbox that's going to come out. So let's just walk through that. You've got 1 foot-pound of torque on the motor, and you've got the force on the teeth, and you've got the various pieces, and you can walk down through all of this thing. And the bearing reaction forces, the couple on the bearings, turns out to be 11 foot-pounds of torque. Okay? And subtracting, because it's a different sense, the 1 foot-pound of the motor, you get the 10 foot-pounds that you need that is actually then on the motor casing. And the significance of this from an engineering point of view is you've got to design the loads on the gear teeth and on the bearings. And of course the structure itself needs to be strong enough such that the load path from your hand, or the handle, through to that gearbox has got to be able to handle that moment and the appropriate forces that make it up. So the real trick here, of course, is that you could take a free body diagram of the drill, then you can sort of drill down, in quotes, to the free body diagram of the gearbox and sum up the moments on the shafts that go in, and then the reaction of the gearbox case. And that's all I'm doing through here. And if it was a right angle drive, you'd have to do the same thing. The point this is this video was trying to show, the design engineer involves going inside the product and tracing the forces and moments through the design product to determine the loads and the nodes that are needed to perform, and then to specify the capacity of the components. And it's essentially just a series of successive free body diagrams as you get smaller and smaller. And that's the point of this video. It's kind of somewhat unique in the sense that people wouldn't be able to tell you the answer to the question I posed early on. You can easily show it. And that systematic way of approaching an engineering design problem is what you need to learn as a design engineer.